So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to my new and a very interesting video. So, as you might have noticed, what we are going to just tackle in this video, and if you are following my videos, you might have an idea about what is that. Let me just write that down here again. That is gamma of z times gamma of 1 minus z equals pi over sine phi z. So this is known as Euler's reflection formula. And if you are following my videos, so you might have watched one of my videos in which I have proved this result using an integral. And what that integral was? Integral from 0 to infinity of x to the n minus 1 over 1 plus x dx. That I have proved it equals pi over sine and pi. I have proved this. I think I took 42 minutes or something like that to prove this. And if you haven't watched this video yet, so just go and watch this, because I have used Fourier series and a lot of things to prove this down. Okay, so now, and actually this integral is also equals to gamma of n times gamma of 1 minus n. It's just gamma transformation, right? You can just have, or maybe it's just beta transformation. I think, yeah, it's beta transformation. It's a beta transformation integral. So we can just prove that down. You can just check that out. My introductory videos on beta and gamma functions. You can have the idea how to just convert this integral into this term. So finally we are here to prove this equals that, rather than this method or this integral, because we did this earlier. So we are just going to use another method, and this is method number 2. Method number 2 to prove Euler's reflection formula. And really, let me just tell you something about this. Well, there are some conditions over there, but I'm not talking about that. Or let me just write that down here. So z is less than and greater than equal to 0. Less than 1 and greater than equal to 0. Sorry, greater than 0 actually. So yeah. So basically we are going to use the gamma function only. So if you haven't watched my introductory video on gamma function, please go and just watch that video, because I'm just going to jump from that video to here and using an integral from that video to here. Actually, it's just the most basic integral of gamma function we are going to use to prove this now. So let's begin this journey, because it's gonna take time, but not that much, I think. Oh, let me just turn off my AC, because yeah. So what was gamma of z? It was integral from 0 to infinity of e to the negative t to the z minus 1 dt. Yeah, right. Okay, so this was our gamma function, right? I have proved this that was equal to z minus 1 factorial in that video, so you can just check that out if you want. Okay, so in one of my old videos, I have proved the Euler's formula, that is e to the I z equals cosine z plus I sine z. So in the proof of in the video in which I proved this, I have told you that e to the minus, let's talk about e to the t, was equals, limit n tends to infinity of 1 plus t over n whole to the n. So it's a representation of e to the t, right? Yeah. Okay, so if I'm replacing t with the negative t, so that's gonna give us e to the negative t equals limit n tends to infinity. This plus will become negative 1 minus t over n to the n. So we are just going to replace t with z for our case. Sorry. We are just going to plug this thing over here, and let's continue with that. So yeah, these two things are prerequisite for this proof. So please just have a look at that, please. So yeah, let's just replace it with that. So gamma of z equals integral from 0 to infinity. This a to the negative t becomes limit n tends to infinity of 1 minus t over n to the n t to the z minus 1 dt. And I can say gamma of z is limit n tends to infinity integral from 0 to n. Well, figure this out. You can just replace infinity with n because eventually n is tending to infinity, so that's not gonna change anything else. So 1 minus t over n to the n and t to the z minus 1 dt. Okay, so now we are having two functions, this first and this one second. Obviously, we are going to use the by parts di method. So let's do that here. So our d and I. Okay. So if we talk about which function to be differentiated at first, so I'm talking about this function. So plus 1 minus t over n to the n is being differentiated and t to the z minus 1 is being integrated. So next would be when you differentiate this eventually, so that's going to give us 1 minus t to t over n to the n minus 1, and when you differentiate inside this parenthesis, so that's going to give us minus 1 over n being multiplied, right? When you integrate this, that's going to give us t to the z over z plus this yeah, so okay, so n over n, and this becomes n minus 1 when you differentiate this again. So yeah, oh sorry, I'm so sorry. N times minus 1 over n, and when you differentiate this again, n minus 1 minus t over n to the n minus 2, and again when you differentiate this, so that's gonna give us minus 1 over n, right? And when you integrate this, t to the z plus 1 over z plus 1, right? Okay. Oh, let me just have a look at here. Is everything is going correct? I think, yeah. Okay. So okay, and again the last one, n times n minus 1 over n squared, because this negative, this counters this negative, so that's going to give us positive 1 minus t over n to the n minus 3 and n minus 2 and 1 over n, right? Again, when you differentiate this whole thing with respect to t, okay, yeah. So okay, wait a second, yeah, that's good. And this becomes t to the z plus 2. Sorry, okay. So z being multiplied here, please just note that down. And this is z plus 2 over z times z plus 1 times z plus 2. And when you do this, this keeps going, right? Okay. So finally, I'm just going to have um, this becomes, at some point this is going to be 0, right? So that is when all these power just comes out to front, and this become, well, let's say that taking wait a second, n times, so that should be n to the n. Okay. Okay, I got it. Okay, let me just write down that here. Please don't get confused, please. And if you have any kind of doubt, make sure to ask in comment section. I will reply that. Okay. So actually, you know what? Like, why this negative 1 over n comes out? To neutralize this negative 1, eventually everything is going to be positive, because this negative and this negative is being neutralized by negative factor. So yeah, that's why it's quite being nested. Yeah, okay. Let's just do this, and this just goes up to, well, look, just have a look at here. If I'm doing this n times, like if I'm just differentiating this n times, right? So here I have to integrate this n times. It means that, oh, wait a second, actually. Okay, so yeah, right. It's getting quite challenging, I think, or else I think I made this challenging, maybe. So I'm differentiating this n times, so I have to add this up to n times, right? So if I'm differentiating this up to n times, so what would be the last term left? That would be n times n minus 1 times n minus 2 dot 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 3 2 1 over n over n over n and dot 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 over n over n over n, right? Because n is just coming up every time, and the last term would be for integral. It would be careful, when it was the power was n, it's z minus 1, so last term would be n plus z minus 1, right? So this oh, wait a second, actually. And again, with differentiating, with division with these denominators, actually I don't have to forget about them also. So z times z, wait a second, I think z times z plus 1 times, I think I should just write that down truly. I just jumped. So our gamma of z comes out to be 1 minus t over n to the n times t to the z over z, okay, plus this becomes n over n z. Wait a second, z plus 1 minus t over n to the n minus 1, this one, right? And okay, t to the z plus 1, t to the z plus 1, and plus, when you just do this to that, so that's gonna give us n times n minus 1 over z, n times z, actually it's n squared, be careful, yeah. So n squared z times z plus 1 times z plus 2 and 1 minus t over n to the n minus 2 and t to the z plus 2, right? And this goes up to integrating from 0 to infinity. Okay, that's good. This is what we're having, right? And if we talk about the last term, so we are having um, this keeps multiplying up to z plus n minus 1 terms actually, right? Yeah, z plus n minus 1 terms. So our finally we would be having n times n minus 1 times n minus 2 dot 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 3 to 1 over n to the n and times z times z plus 1 times z plus 2 dot 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 to z n plus z minus 1. Wait a second. Yeah, an integral from 0 to infinity of t to the n plus z dt. I think it looks quite good. Oh, I'm sorry. Integrating this one only. Oh, I'm sorry. Okay. Again, it's not infinity, it's n. Okay. So then, this comes out to be okay, and n to the n z. Okay, yeah, that's good. And then if you integrate this, so you're gonna have n to the n plus z. That's it. N to the n plus z actually. N to the n plus z over. So this. Oh, wait a second. I'm talking about this one. So when you plug n t equals n in every one of them, so you're gonna have 1 minus n over n, that is 1. So 1 minus n, that's 0. And when you plug the lower limit, so here t would be 0, so everything would be 0. So finally this comes out to be 0 only. So we are left with a gamma of z equals this one, n over n times z times n minus 1 over n times z plus 1 times n minus 2 over n times z plus 2, right? And that just goes up to 1 over n plus z minus 1, and this integral comes out to be n to the z plus n over z plus n. Okay. Oh, wait a second. There was a limit n tends to infinity, so don't forget about that even. So here, limit n tends to infinity. Be careful about that also. Okay. And now, if we talk about to simplify this further, so you're gonna have okay. Wait a second. Let me just erase that one, and then we'll continue here. Actually, the main challenge is to differentiate and integrate a lot of times, and then you have to write them in order to just get some perfect relation. So that's the challenge actually. But it's all right. It's good, and we are left with gamma of z equals limit n tends to infinity of. So if you look at this one, so this becomes n factorial, the numerator, and if we talk about the denominator, so that is n to the n, the product, as it goes up to z minus 1 from beginning with k equals 1 to from of z plus k. So this is, yeah, that's it, and we are left with this one only. So n to the z plus n over z plus n. Okay, and now if we are gonna wait a second, I think then we can say that it's n to the z over z. What's that? Oh, wait a second. Okay. So it goes up to n. Okay, I got it. So gamma of z comes out to be limit n tends to infinity. This n factorial, okay? So this is n factorial over n to the n. The product z minus 1, k goes from 1, z plus k. And this is n to the z times n to the n over z plus n. This n to the n cancels out with that one, and we are finally left with what was n factorial. So n factorial comes out in this part. So okay, so I have to multiply it with that. This becomes, when you just combine these two things, so they are gonna become k equals 1 to n, k equals 1 to z. Oh, this is n minus 1. I'm sorry, n minus 1. K equals 1 to n minus 1 actually, right. Okay, just cool down, and yeah, but where you are having z as factor, I'm just thinking about that. Please guys, just you have to just forward yourself for some time, because this becomes n to the z comes out in front. So where does z comes out to this z. Oh, okay. Again, I got it. I'm talking about this z is out of this. Okay, this z is out of this, and that's what we are talking about actually. I just forgot to write this down. So here we are having 1 over z, and again 1 over z. So finally this comes out to be gamma of z equals limit n tends to infinity of n to the z over z, and times the product as k goes from 1 to n of k over z plus k. Okay. Please just note that down. I haven't included this z right till now, so that's what we are left with here after using that z. Okay, so far so good. And then now we're looking for the recursion formula. You have to note that down for some time, because now we're moving towards the other part to evaluate gamma of the Euler recursion formula. We are going to use the recursion formula for that. So what's the recursion formula says? It says gamma of 1 plus z equals gamma of z times gamma of z. So when you replace z with negative z, so that's going to give us 1 minus z gamma of minus z. So that's what we are going to use here, right? Okay. So firstly, if we talk about gamma of z, it's here, and if we talk about gamma of 1 minus z, so let me just, okay, so yeah, I can just replace z with negative z in order to get this this term. So here I'm just going to replace z with negative z. So gamma of negative z equals limit n tends to infinity, and that would be n to the negative z over negative z. The product it's not infinity but n, as k goes from 1 to n, k over negative z plus k, right? So yeah, this is what we are having. And now we have gamma of z, gamma of z on gamma of minus z. So now we can just have a look at here also. And now if I talk about gamma of 1 minus z from here, so it's just being multiplied gamma of, like it's just minus z is being multiplied to this. So that's gonna give us minus z times limit as n goes from n tends to infinity of n to the negative z over negative z, the product as k goes from 1 to n of k over k minus z. Okay. Oh, let me just have a look at this for my confirmation actually. So yeah. Okay. Okay. So yeah. Now we can just do this in order to get gamma of 1 minus z. And now our final steps comes out, in which we just have to, firstly let me just write that down here. We have evaluated gamma of z to limit n tends to infinity of n to the z over z times the product as k goes from 1 to n of k over n plus k. Oh, sorry, z plus k actually, right? Okay. And gamma of 1 minus z comes out to be limit n tends to infinity n to the negative z product as k goes from 1 to n k over k minus z. So I'm just going to multiply them together in order to get the right hand side of Euler's reflection formula. Okay. So yeah, here we are going to multiply them together. So gamma of z times gamma of 1 minus z equals limit n tends to infinity n to the z over z product as k goes from 1 to n of k over k plus z times limit n tends to infinity of n to the negative z times the product as k goes from 1 to n of k over k minus z. Okay. Okay. Yeah, that's good. And now you can just see that this and this being cancelled out, and we are just left with two terms actually. We can combine these two, like in limit and this product, because they are same, so we can combine them with only one. So limit as n tends to infinity of 1 over z times the product as k goes from 1, and after being multiplied these two arguments, so k over k plus z times k over k minus z. So that says okay, so that says yeah, okay, wait a second wait a second wait a second. Okay, so now we can say that gamma of z times gamma of 1 minus z and times z, this factor, equals limit n tends to infinity of, or let me just write that down with infinity over the top. So product as k goes from 1 to infinity of k square over k square minus z square. So this is one thing that we needed to just have a look. And now onwards we are going to look at the Euler's infinite product for sine function. And that basically says, let me just write that down over here. That's really amazing. Even I have proved that, and if you want, I will bring some video on proving of that because that's really amazing. So yeah, uh, if we look at uh, sine z over z equals the product as k goes from 1 to infinity of k squared over k squared minus z squared. Oh, okay, wait a second. Oh, I'm sorry. I'm not talking about this one, but this z square over k square. So this is Euler's infinite product for sine function. I have I have proved this in my notebook, but I haven't uploaded a video to prove on proving this. But if you request me, or maybe I will just bring a video to prove this down, and it's gonna take a lot of time, like maybe more than 1.5 or some 2 hours to prove this down alone. That's really big. Okay, so yeah, and if I'm going to just okay, so that oh, let's replace z with pi. Let's replace z with pi z actually. Pi z, right? So that says sine of pi z over pi z, right? Equals the product that goes from k equals 1 to infinity of k squared minus z squared over k squared, right? And if you just flip just take the reciprocal of this equation, so that's gonna give us pi z over sine pi z equals, you have to flip this argument instead of this product. So that's gonna give us k squared over k squared minus z squared, and just have a look at that what we have evaluated here. This is the same thing, and hence we just got this. Okay, okay. Please just have a look at this view. This is, let me just write that down here. Euler's infinite product for sine, right? And till now we have concluded gamma of z times gamma of 1 minus z times z equals this product. And from infinite product of Euler's for sine, the product itself equals to this thing. So hence we can say that oh, I think oh, wait a second, I think I did something mistake. I just forgot something. It was pi squared. I'm so sorry about that. It was pi squared here, so it was pi squared. Please just note that down. It was pi squared. I haven't noted down in this page, so I'm so sorry about that. That's what I'm talking about when I replace z with pi z. So here this z would also be replaced with that. So we were not getting the desired result. So, and when you replace it with that, so yeah, okay. And when you replace pi with pi z, so that's gonna just cancel out, because pi square times z square over pi square times k square, that's just z square over k square, right? Yeah, so far it's good, and now it's good. I'm so sorry. Here it was pi squared. So now from there we can say that this equals to this. And let's just do our final step to prove Euler's reflection formula here. So gamma of z times gamma of 1 minus z times z equals pi times z over sine pi z. So finally gamma of z times gamma of 1 minus z equals pi over sine pi z. Hence proved. Wasn't that amazing, guys? You know what, basically I just got messed up at that differentiation part or ti method. Actually, I'm so sorry about that, but still, if you have any kind of doubt related to that, just ask me in the comment section. Use the timestamp actually to tell me whether you are having where you are having problem. So yeah, thank you so much guys for watching this video. If you have got to learn something from this video, just you have to hit the like button, and if you can, then subscribe it for me. Thank you so much for video. Thank you so much for watching this video. Stay tuned for the next video. Thank you so much. Goodbye.